If I had to name the single most impactful thing you can do to make a system faster, it would be caching. Not a better algorithm, not a faster database, not more servers. Caching. The reason is simple. The fastest operation is the one you never have to do. A cache stores the result of an expensive computation so that when the same thing is asked again, you can answer instantly, without going back to the database, without running the query, without doing the work twice. Today we'll cover what caching is, where to put caches in your architecture, the strategies for keeping caches in sync with your data, and the gotchas that trip up engineers in interviews. Caching works because of a fundamental property of real-world data access. Most data is accessed far more often than it is updated. Think about a news website. The homepage shows the same top 10 articles to millions of visitors. Every single one of those requests would normally hit the database. With a cache, the database is queried once, the result is stored, and the next million requests are served directly from memory. This is called the read-heavy workload pattern, and it's where caching provides the most dramatic improvement. The formal concept behind this is called temporal locality. Data that was recently accessed is likely to be accessed again soon. And spatial locality, data near recently accessed data is likely to be accessed too. Caches exploit both. The empirical reality of most production systems is that the top 20% of your data receives 80% of your read traffic. This is the Pareto principle applied to data access, and it is why a cache that holds just 20% of your total dataset can absorb 80% of your database read load. You don't need to cache everything. You need to cache the right things. Twitter's timeline service is a classic example. When a celebrity with 50 million followers posts a tweet, that tweet could trigger 50 million database reads within seconds. Twitter pre-computes the timelines of highly followed accounts and pushes the data into cache before users even request it. When users open their timeline, the result comes from cache, not from a chain of database joins. The result is sub-millisecond feed loads at a scale that no relational database alone could support. Caches can exist at multiple layers of your architecture. Knowing where to place them, and why, is a key part of any system design answer. At the top of the stack, you have client-side caching. When your server responds with proper HTTP cache headers, cache control, etag, last modified, the browser stores the response locally. On the next request, it might not even go to the server at all. This is why a modern web page loads much faster the second time you visit it. Assets like JavaScript, CSS, and images are already cached in your browser. The etag mechanism is worth understanding precisely. The server sends a hash of the resource content in the etag header. On the next request, the browser sends that hash back in if none match. If the content hasn't changed, the server responds with 304 not modified. No body, just a header. The browser serves the cached version. This eliminates bandwidth cost while still validating freshness, which is the right trade-off for assets that change occasionally but not constantly. CDNs are a form of geographic caching. They store copies of your static content, images, videos, style sheets in data centers around the world. When a user requests an asset, they're served from the nearest CDN node rather than your origin server. For large-scale systems, CDNs are non-negotiable. They reduce latency, reduce load on your origin servers, and provide DDoS protection through sheer distributed scale. Netflix uses CDNs so aggressively that over 90% of their video traffic never touches their origin servers. They work with ISPs to place CDN nodes inside internet service providers' own data centers, as close to end users as physically possible. This is called an Open Connect appliance. When you stream a Netflix movie, the video bytes may be coming from a server physically in your city, hosted inside your ISP's building. The round-trip time is measured in single-digit milliseconds. That is only possible through extreme geographic caching. The most important cache in most architectures is the application-level cache, a dedicated caching layer, typically Redis or Memcached, that sits between your application servers and your database. Your application checks the cache first. If the data is there, a cache hit, it returns immediately. If not, a cache miss, it queries the database, stores the result in the cache, and returns it. The next identical request is a cache hit. Redis versus Memcached is a question that comes up in interviews. Memcached is simpler and marginally faster for pure key-value caching workloads. Redis supports richer data structures, sorted sets, lists, streams, pub, sub, and persistence options. For new systems, Redis is almost always the right choice because the additional capabilities are valuable and the performance difference is negligible at normal scale. Use Memcached only when you have a specific, benchmarked reason to. Here's the hard part. Caching creates a consistency problem. Your cache has a copy of the data, and your database has the source of truth. When the database is updated, the cache can become stale. How you handle this is called cache invalidation, and there are several strategies. Choosing the right one is often the most interesting part of a caching discussion in interviews. Phil Carlton famously said that there are only two hard things in computer science: cache invalidation and naming things. It sounds like a joke. It is not a joke. Cache invalidation is genuinely hard at scale, and the failure modes are subtle and insidious. Cache aside is the most common pattern. The cache is populated on demand. Only the data that gets requested ends up in the cache. This is memory efficient, but means the first request for any piece of data is always slow, cache miss, and the cache can serve stale data if the database is updated without the cache being told. The typical mitigation for staleness in cache aside is TTL. You set an expiry time on each cache entry. When it expires, the next request gets fresh data from the database. The art is choosing TTL correctly. Too short, and you defeat the purpose of caching by constantly fetching from the database. Too long, and users see stale data for an unacceptably long time. The right TTL depends entirely on how often your data changes and how much staleness your users can tolerate. Write through keeps the cache perfectly in sync by writing to both the cache and the database on every update. No stale data, but every write is slower because you're writing to two places. Write through is best when your access pattern is write data, then immediately read it back. User profile updates are a good example. A user updates their display name and expects to see the new name immediately on the next page load. Write-through guarantees that consistency. The cost is write amplification. Every database write is also a cache write. For write-heavy workloads where most cache data is never read again after being written, write-through wastes cache space and introduces unnecessary latency. In those cases, cache aside with TTL is more appropriate. Write behind is the fastest option for write-heavy workloads. You write to the cache and return success immediately, then the cache asynchronously persists to the database. The risk is obvious. If the cache crashes before the async write happens, you lose that data. Write behind is used in scenarios where maximum write throughput matters more than strict durability. Analytics event ingestion, game leaderboard updates, social media engagement counters. For financial transactions or medical records, the data loss risk makes right behind completely inappropriate. Two more concepts to lock in before we talk about cache failure patterns. TTL, time to live, is the expiry time you set on a cached item. After the TTL expires, the item is evicted from the cache. The next request is a cache miss and fetches fresh data. TTL is how you handle stale data without building complex invalidation logic. If your product prices change every hour, set TTL to 60 minutes. Stale data lives at most 1 hour. Choosing TTL correctly is an engineering judgment call that depends on your data's volatility and your consistency requirements. For session tokens, TTL might be 24 hours. For stock prices, TTL might be 1 second. For a user's profile photo, TTL might be 7 days. There is no universal answer. The right TTL is the shortest time you can tolerate stale data for, balanced against the database read pressure that short TTLs create. When a cache runs out of memory, it has to evict something to make space. LRU, least recently used, evicts the item that hasn't been accessed for the longest time. The intuition is that recently accessed data is more likely to be accessed again soon. LRU is the default in Redis and Memcached. It works well for most workloads. LFU, least frequently used, is better when some items are permanently hot and you don't want them ever evicted. There is a known weakness of LRU called cache pollution. If you scan through a large dataset, say, running a bulk export job that touches every user record, LRU will evict your actual hot data to make room for the scanned data that will never be requested again. For scan-heavy workloads, LFU is more robust because frequency is harder to game than recency. Redis supports multiple eviction policies: all keys LRU, volatile LRU, all keys LFU, volatile LFU, all keys random, and no eviction. In interview answers, knowing that Redis has configurable eviction and being able to explain when you would choose LRU versus LFU puts you ahead of most candidates. 3 cache failure patterns come up constantly in interviews. You need to know them. The mitigations for each of these are as important as the definitions. For cache stampede, the mutex lock approach has one process acquire a lock to rebuild the cache while others wait. Probabilistic early expiry starts refreshing a cache entry slightly before it expires, based on a random probability that increases as the TTL decreases. Background refresh schedules an async cache refresh job before expiry, so the cache is always warm. For cache penetration, caching null results is the simplest fix. If the database returns nothing, store a null sentinel in the cache with a short TTL. Bloom filters are more elegant. A probabilistic data structure that can definitively say this key does not exist in the database in O1 with 0 false negatives. Any request for a key the Bloom filter rejects never reaches the database at all. For cache avalanche, adding random jitter to TTL is straightforward. Instead of setting TTL to exactly 3600 seconds for 1,000 cache entries that were all populated at the same time, set TTL to 3600 plus a random value between 0 and 300 seconds. The expirations spread across a 5-minute window instead of hitting simultaneously. Here is how to discuss caching correctly in a system design interview. Step 1. Propose caching proactively. Do not wait for the interviewer to suggest it. When you establish that your system is read-heavy, say, given the read-to-write ratio, I'd introduce a cache layer here, Redis, between the application tier and the database. This should absorb the majority of read traffic. Step 2. Specify what you are caching and why. Vague answers fail. Good answers sound like: I'd cache the user profile object, the follow account, and the pre-computed timeline. I would not cache real-time inventory data because the consistency requirement there is strict. Step 3. State your invalidation strategy and justify it. For read-heavy data with tolerable eventual consistency, cache aside with a 60-minute TTL. For data that must be consistent immediately after a write through. For maximum write throughput on non-critical data, write behind. Step 4. Mention the failure modes. Name at least 2 of the 3, stampede, penetration, avalanche, and state their mitigations. This is the detail that separates a senior-level answer from a mid-level answer. Most candidates know what a cache is. Far fewer know that cache stampede can take down a database that the cache was supposed to be protecting. Step 5. Address cache sizing. How much data do you need to cache? A system design answer that includes, I'd cache the top 20% of data, roughly X gigabytes, and configure Redis with Y gigabytes of memory, sounds far more credible than I'd add Redis. The target hit rate in production systems is 95% or higher. If you are consistently below 90%, your cache is either too small, your TTL is too short, or you are caching the wrong data. These are the caching numbers that should be second nature in any system design conversation. Memory latency versus storage latency. Reading from RAM takes roughly 100 nanoseconds. Reading from an SSD takes about 100 microseconds. Reading from a spinning disk takes 10 milliseconds. Reading from a remote database on the same network takes 1 to 10 milliseconds. A cache hit on Redis returns data in under 1 millisecond, typically 50 to 200 microseconds, including network round trip within a data center. These are the numbers that explain why caching matters. Redis throughput. A single Redis instance on commodity hardware handles over 1 million operations per second for simple get-set operations. This is a number worth memorizing. Your database handles a few thousand to tens of thousands of queries per second. Redis handles 1 million. The difference is an order of magnitude. That gap is what makes caching so effective at absorbing load. Memcached throughput is comparable, also in the range of 1 million operations per second. But Redis's richer data structures make it the standard choice for new systems. Cache hit rate targets. Production systems aim for 95% hit rate or higher. Facebook's Memcached infrastructure reportedly maintains a 99% hit rate across billions of daily active users. At 99% hit rate, your database sees only 1% of read traffic, 100 times reduction in read load. Cache size guidance. In practice, caching 20% of your hot data absorbs roughly 80% of your read traffic. A medium-sized production Redis deployment, 16 to 64 gigabytes of RAM, is sufficient for most applications at millions of DAU. At the scale of Twitter or Meta, Redis clusters span hundreds of nodes with terabytes of aggregate memory. Redis persistence options. By default, Redis is purely in-memory and loses data on restart. Redis append, only file, AOF. Persistence writes every command to disk. Full durability, roughly 10% performance overhead. Redis RDB snapshot persistence saves point-in-time snapshots. Faster, but risks losing the last few minutes of writes on failure. In most interview scenarios, you should mention that your Redis cache is configured without persistence. If the cache goes down, you rebuild from the database. Cache loss is tolerable. Cache inconsistency is worse. Round-trip time context. Within a single AWS availability zone, A Redis GET call takes 50 to 200 microseconds. A PostgreSQL query on a warm index takes 1 to 5 milliseconds. Caching makes the common case 10 to 50 times faster than the database, not just marginally faster. Caching is the most powerful performance tool in a system designer's toolkit. The key decisions are where to cache, which invalidation strategy to use, and how to handle the failure modes. For interviews, mention cache aside. For read-heavy workloads, mention TTL. For staleness management, mention the 3 failure patterns: stampede, penetration, avalanche, and their mitigations. Quote, the 95% hit rate target and the 1 million operations per second Redis benchmark. That combination puts you in the top tier of candidates. Notice the pattern building across these first 4 videos. Horizontal scaling creates the need for load balancers. Load balancers enable you to add application servers without limit, but every additional application server generates additional database read-load. Caching is the answer to that read-load problem. These concepts are not independent. They are a system that fits together. In the next video, we tackle databases, specifically the SQL versus NoSQL decision, which is one of the most common questions in system design interviews. It is also one of the most commonly fumbled, because candidates default to saying NoSQL for scale without understanding what they are actually trading away. We will fix that. See you in video 5.